Ladies and gentlemen, in this talk we'll finish the basics of molecular dynamics. The Verlet method or the leapfrog method, they are equivalent, are the method of the first choice for molecular dynamics. I would say that 90% or even more of the code available runs Verlet or leapfrog. But there are also other options. One option is the so-called predictor-corrector type. Here we must know a history, certain number of points in the history which we use to predict an approximate solution. There are several types of predictors. The Gears predictors are the simplest ones. They simply take a polynomial and predict this value. Such a prediction using a higher order polynomial is very imprecise, but still it is useful. If we know this predictor will calculate the right hand side, and we have two values. We have the predicted forces, because if we have a predicted trajectory, we have predicted forces too, and we have the forces which are calculated at this predicted point, and we compare them. And there is certain difference between these two values, and we use this difference in a very smart way how to correct this trajectory, how to calculate a corrected value. For the first glance, one would have such a type of reasoning. We use more information here than in the case of the Verlet method. Then there is a chance that our method will be more accurate. More information, more accuracy. To some extent this is true, but it depends on what's accuracy. In molecular dynamics we are interested in the behavior of the total energy, that is potential plus kinetic. But unfortunately these methods are not time reversible, and it means that the energy conservation is poor. It means that there is a trend, a drift in energy. Usually we don't like this. On the other hand, there are pros for this method too. I will show you now a trajectory of a planet revolving around a star using the Gears method of the fourth order, and you can see that the perihelion does have a small precision, but lower than the similar method, the Verlet method, but the energy decreases. In chemistry, when energy goes out, we don't like it. This is a higher order Gears method. And this is an even higher order method. It is quite accurate as regards the ellipse, but still the energy changes a bit. These methods are sometimes used, for example, for rotations. The fact that they are not time reversible doesn't matter so much if we use a thermostat anyway. To compare the Verlet method and any method that is equivalent, that is leapfrog or velocity Verlet and so on, is time reversible. That is, there is no drift in the total energy. But it's even better, it's symplectic. That is, the error in the total energy is bound. Here you can see, it was also in the end of the last lecture, the difference between a reversible method, there is no trend, but still the fluctuation is larger, and a symplectic method, the red one. But there are disadvantages of the Verlet method. They are of a low order, that is, they have quite a large phase error. Usually we don't mind if the frequency of a harmonic oscillator is a bit shifted, it doesn't matter. But they are directly not applicable to the equations which contain velocity in the right hand side. the basic Newton's equations don't contain velocities in the right hand side. They are of the type that we calculate the forces and then the acceleration just from positions. But in some cases we have such terms. For example, if we use rotating bodies, constraint dynamics in some cases, or some types of thermostats. I will speak about this later. Also, it's difficult to change the time step, but usually this is not a big problem. We usually keep the time step fixed in molecular dynamics. The Gears methods are just opposite in all these aspects. That is, they are not time reversible, they are of higher order, they can be applied to these equations, and it is easy to change the time step. Here you can see graphs of sample simulations. This was liquid argon, I guess, and the total energy, that is kinetic plus potential, with different time step sizes. It can be seen that this is the longest time step, 2 femtoseconds. The fluctuations are quite large, but still it fluctuates around a certain value. With half the time step, the fluctuations are about 1/4 of this, because it's a second order method, and this is a very tiny time step with very small fluctuations. The Gears method work well if you have a very short time step, and have trend if our time step is longer. This is a higher order Gears method, and this is a very high order Gears method. It is very accurate if we have very short time step, but with such a long time step it doesn't work well. So it was enough for the Gears method, and now what about the temperature? So far we integrated the equations of motion, and what we got was a system which was microcanonical and which conserved the total energy. If we have such a system, we still can calculate temperature. We simply take the kinetic energy and divide it by this value, where F is the number of degrees of freedom. If you remember, 1 degree of freedom on average has the kinetic energy 1/2 of the Boltzmann constant times temperature. So that's why this formula. These angle brackets mean averaging over time during the course of the simulation. The question is, what exactly is this number of degrees of freedom? Approximately, if we have n atoms of argon, we have 3n degrees of freedom. But it's not precise. Sometimes we have some degrees of freedom conserved. For example, let's have a spherical cavity. It's not a popular way how to conduct simulations, but we can imagine it. Then what is conserved is 1 for energy, sometimes it is not counted, and 3 rotations. Usually such a simulation is run in such a way that this rotation is set to 0, that is, the angular momentum is set to 0, then it is conserved. There may be tiny fluctuations which then can be once a while adjusted to real 0. But when we calculate the temperature, we use the number of degrees of freedom where these conserved degrees of freedom are deducted. It is sometimes useful to calculate separately the temperature from velocities of the centers of mass and from rotations and other internal degrees of freedom. They should match. If they don't, it means there is some inaccuracy or some other problem. It is much more convenient to have a constant temperature. It is the same as in a real experiment. In a laboratory, you use thermostats to set temperature to a constant value. So we would like to have a thermostat also for molecular dynamics. And there are several types of thermostats. Some of them are not canonical. It means that they do not give the true canonical ensemble, although they do give the correct average temperature, or kinetic energy corresponding to the correct temperature, I mean. The canonical ensemble means that all configurations have probabilities to occur in the trajectory proportional to the Boltzmann probability. These thermostats which are not canonical do not have this property. Often it doesn't matter. Sometimes we need quantities like fluctuations, and then it does matter. We cannot use these methods to determine some quantities. The simplest method of this type is velocity rescaling. You know that the kinetic temperature is proportional to the kinetic energy, and it is proportional to the sum of velocities squared in some way. There may be some constant here. Okay, so if our kinetic temperature determined from here differs from the thermostat temperature that we want to have, the temperature T, we simply get the correct scaling factor and multiply all velocities here by the same factor, and if we do this, we at this moment get the correct kinetic temperature. But this procedure affects the trajectory a lot, so it's not a good idea to do this in such a straightforward way. It's much better to do it only gently. Instead of the square root here, we can use certain other factor q, which is smaller and much smaller usually than 1/2. It means that during every step we modify the velocities only a bit, but in the correct direction. And during the simulation we are doing many steps, and the temperature eventually fluctuates around the correct value. This method is called the Berenson method, also a friction thermostat or something like that. We can rewrite these equations to true equations of motion, but it's not important. It's a technical detail. Then we have canonical deterministic thermostats. The most best known thermostat is the so-called Hoover Thermostat. The trick is that we add a degree of freedom to the system. A degree of freedom, you can imagine an imaginary particle with 1 degree of freedom in 1 dimension with a special potential energy and a kinetic energy. If we do this in a very smart way, this new degree of freedom will fluctuate, and on average we'll get the canonical ensemble of the whole system. But there is no free lunch. There are problems with the Verla method, because this equation of motion here contains the right hand side which depend on velocities. So either we must do some tricks or we can use the geared methods. There is also a modified Berenson method in a smart way that will get a canonical ensemble, but it is not widely used, as I know. And then there are stochastic thermostats, and these are usually canonical with a high precision. Stochastic means that we use random numbers or random motions. One type, the so-called Maxwell Boltzmann thermostat, means that we run a normal microcanonical simulation, and once a while we stop it keep the positions of our particles, but use new velocities, which are drawn from the correct Maxwell-Boltzmann distribution at a given temperature. There are some formulas for this. I will not derive them here. It's not important. Of course, if we use such a thermostat, we cannot study quantities like, for example, diffusion or viscosity, because the trajectory is affected a lot. But we can study all static quantities. There is a more gently way how to do this, that is to randomly visit particles. It is usually better. That is, we run a simulation, and once a while with certain probability we visit any randomly chosen particle and change its velocity. But there is even a finer way how to do it. It's the so-called Langevin method, and this is based on modifying the equations of motion by adding a random force. This random force is added to all particles at every step, but it must be really small. And if this force has the correct properties, we'll get a thermostat. We must combine a random force edit, because such a process adds energy to the system, and a sort of friction, like this term or this term, because we must cool this system because of this energy edit, and we must balance these two actions to get the correct temperature. There are formulas for this. There is also a quite popular method called canonical sampling through velocity rescaling, and it is essentially based on the Berenson idea, but this exponent q, or this parameter eta in this formulation, is stochastic. It is given by a certain equation of motion, so that the resulting system is to some sense stochastic, but the equations of motions are affected only a bit. So this is essentially almost deterministic system as regards trajectories. And there are some other methods which are not so important. Here with a plus, it means it's something not so important. If you are curious how such a degree of freedom added to the system in the Hoover Thermostat looks like. The kinetic energy is quite fine, and the potential energy is here. F is the number of degrees of freedom. And these are the equations of motion, the modified ones. You can see that in the right hand side we have velocities. Now a comparison of different thermostats. Usually the Hoover thermostat is regarded as the best, with the highest quality, because it is canonical. It's also good for very small systems, especially if we combine several of them. It is a so-called Hoover chain. As regards disadvantages, the time constant of the thermostat, or the mass of the degree of freedom, simply a parameter that controls the coupling between this additional degree of freedom and our system, must be quite fine-tuned. If it's not, it doesn't work. Either it oscillates, or the equations of motion are broken, and if these artificial motions are too fast. And also a technical problem with the equations of motion with velocities in the right hand side. The Berenson thermostat is simple. It is very good at start. If our system is far off equilibrium, it exponentially fast relaxes towards the equilibrium. So it's a good idea to start, for example, with Berenson and continue with Hoover. And the stochastic thermostats are canonical, they have exponential relaxation, but there is a problem. The kinetics is lost or not precise. They are also problematic if we have a system with bonds, for example. But what I skipped is the problem with the balance and thermostat, the so-called flying ice cube problem. And it is poor for small systems. And I will show you now the flying ice cube problem, but unfortunately I don't have it prepared. So I do it in such a way. Here I have a simulation system. I use a periodic system, decrease the number of particles. Now I decrease temperature. There is a balance and thermostat, so I put this constant to a low value. Also I decrease the density, and also you can see it. The system which now I have prepared is a crystal. Crystal, or at a bit higher temperature, a droplet of liquid, but instead of a crystal with thermal fluctuation, I can see that the system starts to rotate. And of course it is wrong. This artifact is called the flying ice cube artifact. We don't like it, but if we have a system in the periodic boundary conditions, it doesn't matter. I will now switch to Monte Carlo, which essentially makes my system without any rotation. I increase the bit temperature. I also increase the number of molecules more. Decrease again, and they all switch to the Barenthal method again. So we can see this problem for the second time, but I must decrease the temperature a bit because otherwise I have a lot of vapor. And after some time, it's a random process, it depends on start, we'll see instead of a droplet of liquid that the system freezes and rotates. That is all. Random thermal motion is changed into rotation. Bad thermostat. Here is an example of application of thermostats to water. I took 250 randomly oriented water molecules and ran a simulation with different thermostats. The starting system was such a lattice. It's not a crystal of ice. There are randomly oriented molecules, and I have it shifted it a bit here. So I return back. Here is how it looks like. This is the start. It is regular, and during simulation by 10 femtoseconds, by 5 times that we can see how the simulation looks like. This was the balance and thermostat. So I return back here, and what we can see using the balance and thermostat means that the temperature relaxes fast to the temperature of about 300 Kelvin, which is the target temperature. This is the standard balance thermostat. We can see here 3 curves. The black one is the total kinetic temperature. The red one is calculated only from the center of mass, and blue from rotation. So we can see also that these two types of degrees of freedom relax very fast. They should, of course. Here is the balance thermostat applied only to the internal degrees of freedom, so it's slower. This is applied only to the center of mass. Again, it is slower, but it eventually relaxes. Here is the Hoover thermostat. You can see that there are such oscillation. They are damped, so after some time we would reach the correct temperature too. But if the initial system is far from equilibrium, this is not a good thermostat. This is a Maxwell Boltzmann thermostat applied to the center of mass. We can see that every 0.1 picosecond there was a reset of all degrees of freedom, so there are jumps here, but it works too. And this is the Anderson thermostat applied to the center of mass, a similar one, but I visit molecules randomly once a while, so it works essentially in a similar fashion. I don't have the Langevin thermostat here, but we'll see it later. You can try molecular dynamics by yourself. I have written computer code called Simulant that is exactly created for teaching for you. To find it, the fastest way is to write Simulant into Google, or here is the link. You download the package according to your operating system. This is for Windows, and unpack it somewhere. But you should create a folder and to unpack this into a folder, because if you ran this just from the web, the Windows system would create a temporary directory and you would have problems with finding files that are written there. So first create a folder and then unpack Simulant there. There are two files there, an executable and a help. And then run it. It's also available for Linux and Mac OS. So let's try. First, let's check the energy conservation. So here is a system in the periodic boundary conditions. It's a gas, and now it's running under thermostat. The temperature is 2 in certain units, and I first check this to get the integral of motion convergence profile. So here convergence profile should appear, but there is no integral of motion for the Benson thermostat. So we must switch to molecular dynamics without a thermostat, which is here. Also, it's a good idea to speed up a bit. And now the system writes the values of kinetic and potential energy of this sum, and you can see that the standard deviation is quite small. Also, this is minimum minus maximum. The graph is always scaled minimum maximum. So it looks like the energy is pretty constant. There are small fluctuations, they should be, and the system uses this time step which has been set up by certain rules. So let's try to change the time step. Let's use a shorter time step, something like this. That is, we'll write here to this window dt equals, and immediately you can see that we have a new level. Now it expanded, and also the molecules move slower because the time step is shorter. So we can go to a longer time step, longer than is the recommended one. So we can see some fluctuations, and still it sort of works. But there was a jump, so it suggests that for this value of the time step, the reversibility isn't so nice, that it's at the edge of good working. So there are a couple of steps here, so the energy increases and the temperature increases too, and the situation may worsen. So the time step of 0.02 doesn't look so well. Sorry. So let's try dt is 0.025, even longer, and it doesn't look well, and I guess after some time, just by chance, two molecules kick each other in such a way that the energy will increase a lot and it crashes. Crashes, it means that the velocity of a molecule is so large that it goes out of the box or over several boxes and so on, and the system will likely switch into Monte Carlo. And also the fluctuations are now much larger. There is a problem with showing this because this is a stochastic process, so you never know whether such a problem that I have announced will occur within 10 seconds or 5 minutes. Well, it's just now. Okay, so it failed, now it starts to restart, but still the energy is high, so it may repeat. So I will return into the default. So this was energy conservation in the NVE ensemble, that is the microcanonical ensemble. We saw that it depended on the time step. If we have a short time step, it was very accurate, but it was inefficient because we needed many time steps. So let's go now to thermostats, and according to the hints here, we change the parameters. So let's do it. Show energy enthalpy convergence profile. So now it's changed. It has a different type of fluctuations because it's not constant anymore. It's the potential energy now for that NV ensemble. But if we change the method into the Berenson, here we have again the total energy, that is the internal energy. It fluctuates. Okay, so let's try different thermostats, and also let's change this tau. In the previous we had tau very short. You can see that if tau is longer and longer, this is 10 of time units, the fluctuations are long. Here the fluctuations are short, so there's certain good value which could be here about 0.3, 0.5 or something like that. So let's try with this value the Hoover thermostat, and you can see that it looks pretty different. First, the standard deviation, it was written here, is larger, and this is the true canonical ensemble. And you can see that there are oscillations corresponding to this typical time, and these oscillations interact in some way with the system and create the canonical ensemble. So here, if I shorten the time step, the correlation time of the thermostat, not the time step, is the default one. This is quite shorter and would be a better thermostat now. And here it would be very, very long, so I wouldn't recommend this. It apparently causes artifacts, so this is not good. Let's return back here. Maxwell Boltzmann thermostat, you can see that there are random jumps, and also we can see that molecules sort of diffuse. Again, if I increase the typical time, these occurrences of kicks to all molecules don't happen so often. Let's try the Anderson thermostat. There are kicks too, but only to small molecules, and here it is between the normal trajectory and chaotic Brownian motion, so we can choose the coupling between this stochastic thermostat and the system. Similar is the Langevin thermostat with random forces. We can see that molecules do not move along straight lines, but by affected by random forces, and together it gives thermostat. Again, with a short time, it does something. With a long correlation time, it looks more like dynamics. I have also the Busse thermostat, that is a balanced thermostat with smart scaling factor, so that it is canonical, and it is actually pretty good. It's good enough also for cooling a system which is very hot, and a good thermostat along with the Hoover if we know how to use it. Okay, and that's it for now. Thank you for your attention.